Thank you. So, yeah, thanks for the opportunity to give a talk at this workshop. And my title is Three-Dimensional Gravity Revitalized, which, as you may know, is a play on Witten's title of his 2007 paper, Three-Dimensional Gravity Revisited. And so there's been a lot of action on the 3D gravity front. I wouldn't say it necessarily needs revitalizing per se, but it was just a fun title to make. But I actually will give a different kind of perspective on where I think we can take 3D gravity than the one that was, say, discussed last week in Thomas Knight's lectures, although they're somewhat similar and I'd say compatible, and I'll come back to that later. So this is based on work with my student, Gabriele Di Ubaldo, to appear soon. And so what is the goal? The goal is to, well, answer the old-fashioned question, can we construct a semi-classical, pure 3D gravity path integral that checks all the boxes? So today I'm going to try to construct this path integral, and I'm going to just look at single boundary contributions, and in particular, we'll take the boundary to be a torus. So we'll be looking at the torus partition function of the dual putative 2D state. And so when I say pure 3D gravity, what this means, among other things, is that we want to find at least a candidate partition function where the gap to the first primary state with respect to the extended parallel algebra scales like the total central charge over 12 at large C. And this should be true in leading order in large C. So this question has been asked many times in many ways over the past 15 years. And of course, from the Bootstrap point of view, is the focus or the kind of ambition of the modular Bootstrap extrapolated to large central charge. So if we draw the kind of spectrum that we're after, the vacuum is down here at delta equals 0. And what we'd like is something like this, where above the gap we have lots of states and eventually some Carty growth for delta much greater than C.
Hey, can I ask a question?
Please.
You are allowing for a large compact space, right? Or not necessarily?
Good question. So I'm agnostic about that, but the shorter answer is no. So when I say pure 3D gravity today, I mean has an Einstein gravity description in 3 dimensions, not more than 3 dimensions, as would be the case for a large compact space. And so, indeed, I think the pure 3D gravity endeavor is usually kind of talked about like in a vacuum with respect to some other questions we ask in holography, like the scale separation question. But I think it should be thought of in that sense, where we haven't even been able to construct or verify the existence of a partition function which doesn't have lots of states of dimensions of order 1 in holographic CFT. The canonical examples have these large compact extra dimensions in the bulk, giving rise to these light states. And so even something that's not pure in the strictest sense, but has, say, some sporadic number of light operators, as opposed to some KK tower of them, would be really nice to construct. But not even that's been done. Today we're going to stay with the strictest definition of pure gravity, but I'm glad you asked the question because I think we should, perhaps allow ourselves to relax the conditions a bit, or at least think of it in the context of that problem.
But for this, it's possible that the CFT doesn't exist.
Yeah, definitely. Yeah. And I don't think I need to necessarily remind this audience that from the modular Bootstrap point of view, satisfying S invariance and extrapolating to large central charge, the best bound so far is something like C over 9.1. Sorry. Well, yeah, let's just scale. All right. So we want to do better.
It doesn't get better.
Yes, excuse me. That's, well, let's see. Yeah, that's what I meant. That's what I meant to do. Excuse me. Excellent, thank you. People are paying good attention, and I'm not. Okay, good, thanks. So that's the best we can do by extrapolating the modular bootstrap in its current form out to large C, but we'd like to be able to do better. And from the gravitational point of view, there are various mysteries associated with this. So, you know, among the consistency requirements, we'd like to demand a partition function which is unitary and as such is invariant. Which is the foundation of the modular bootstrap problem. But from the bulk point of view, there's a kind of argument that this should be possible, but there are also questions about how exactly you go about computing this path integral. And especially in the case of multiple boundaries, there's been evidence that summing over saddles may not be the complete answer, or may not give you a fully consistent answer, something I'll review a bit later. And so there's a question whether there exists a gravitational path integral in the semi-classical theory, which does not include off-shell configurations. So even for a single boundary, there have been some proposals that one should include non-solutions and fluctuations around them. Say some work by Eberhardt, some work by Maxfield and Teriachi, some work by Kotler and Jensen. But it's not clear whether even for a single boundary one should really have to do this, and what the rules are, even in the semi-classical limit. So the question of whether you can just sum over saddles or whether you have to do more is one of the questions that I'm going to address, and it's still an outstanding question in the book. So let's write that. Consistent, which we can take to be unitary, modular invariant, and perhaps other things. We'll return to this throughout the talk. Now there's a second question, which is, if so, if you can write down such a thing, a large central charge, say in the semi-classical expansion in the Newton's constant, then how do we interpret it? Do we interpret it as dual to an ensemble average of CFTs? If we do, is that average defined in a conventional sense or in some generalized way? Because after all, if we just make some abstract plot of the space of Virasoro CFTs at some fixed central charge, I think the reasonable expectation is that this is a rather sporadic, wild space. Maybe there are some islands of finite extent, but there'll be lots of points. And so what might we mean by averaging over this space if there are no moduli in the partition function that we're trying to reproduce, and if the space itself is disconnected and there's no obvious sense of a measure on this space? Now, the point of view of some recent work, some of which Tom talked about last week, is that perhaps we don't need to talk about the microscopic space of theories at large central charge. Perhaps there's a sense in which these gravitational path integrals are computing the answer to a different kind of bootstrap problem, tailored for large C. But the ultimate question would like to make contact with the space of bona fide CFTs. Okay. So if this exists, does it only exist in the sense of an average? And if so, what kind of average? And if not, well then can we construct the thing?
Eric,
Yes.
can you define what you mean by regraph without off-shell configuration?
Sure. So
More precisely?
yeah, that's simpler to define than what I mean with off-shell configuration. So let us enumerate the classical saddles of the bulk theory with some fixed boundary condition, and sum over them and all the fluctuations around.
But
That's the traditional way to try to compute. So that's the simplest answer. And indeed, with torus boundary, all these smooth saddles have been classified. And there's some non-smooth ones, some of which are nicer than others. You can add those if you'd like. That starts to get away from what you mean by pure gravity, as you know. But that's, at this point, that's what I mean.
But they only, for example, only include real saddles.
Sure. So right, there's a question of which ones you include, and so yeah, I'm not committing to anything yet, but you're right to point out that there are different definitions, even without optical configurations, of varying degrees of acceptability. And if you include complex saddles, then perhaps you'd like to identify a criterion about which ones to include. So there are still options even without doing that. And so they range from simple to more adventurous. So, to say it another way, what problem is semi-classical 3D gravity solving? Is it really the solution to a Bootstrap problem extrapolated to a large central charge, or is it the solution to some kind of coarse-grained or averaged Bootstrap problem? And so, what I'm going to present today is an answer to this question, which is yes. If you take the chiral algebra to be slightly larger than pure Virasoro, namely u1 to the d times Virasoro. And the sense in which I mean that the answer is yes will become clear as the talk goes on, but the calculation itself is a rather simple extension of things that have been done before, and we're observing that if you add some currents, a lot of the problems are fixed to all orders in a semi-classical expansion. We can give a microscopic interpretation of this, we'll do this at the end. This raises some interesting subtleties, and it comes back to the question of whether we're actually solving the Bootstrap problem at large C, as usually formulated, or a different kind of Bootstrap problem which is separated from the usual one by a kind of non-perturbatively small effect which puts it in the swampland. Okay. Yes?
So when adding this chiral algebra, you're adding some currents to the theory itself. So do you reconcile this with a new notion of, well, I mean a specific notion of pure gravity? Because in principle, classical pure gravity, I guess it really shouldn't have currents. How is this interpreted in this case?
Yeah, good question. So whenever we study a CFD, we should really talk about the spectrum with respect to the maximal chiral algebra. Mm-hmm. And to me, the most pure of the pure theories of pure gravity just have Virasoro symmetry. But I would call any theory of 3D gravity a theory of pure gravity if, for a given chiral algebra, there is nothing up to C over 12 in the primary spectrum with respect to that chiral algebra. And that's the sense in which I'm talking about this today. To say it another way, we are adding something to the theory, but they are all purely boundary modes. This is not matter in the sense of having local degrees of freedom in the bulk. And with respect to this algebra, you can construct a partition function which checks the boxes. Is there another question? Yeah.
So maybe you'll come back to this later, but U1 here is assumed to be non-compact?
I will come back to this later, and it will bring us in contact with your paper about the twist gap. Yeah, in the large C limit, yes.
Okay.
Yes. Okay. Yeah, I definitely invite more questions as we go along, so please keep them coming. And yeah, in the end, the calculation is relatively simple, especially for those who are familiar with the older ones. And so part of the point of the talk is to give a different perspective on what we should shoot for and what we mean when we say we're trying to construct a semi-classical partition function. So let me give a little bit of the history and prehistory of this story. I think this is well known to a lot of people, so I will try not to belabor it. Please ask questions if you have them. So the first paper that must be mentioned is the black hole fairy tale paper from the early 2000s, where what they computed was the elliptic genus of the D1, D5 system. And they showed that it can be written as a sum over smooth classical saddles. In the bulk, which can be written as ADS3 times S3 factors and their modular images there. So the D1D5 system is dual to ADS3 times S3 times T4 string theory. In the supergravity limit, you have this ADS3 factor, you have an S3, which gives rise to an infinite tower of light KK modes from the 3D point of view. And so they showed that given the known formula for this thing, it can be rewritten in gravitational language as an SL2Z sum over saddle points dressed by particles coming from the S3. So you have the sum over all the known BTZ black hole solutions dressed with light states, but not too many such that they form a black hole. The black hole is already accounted for, and you dress it with the perturbative fields coming from the S3. Okay. So this was, at large C, an equality that they derived. And I'd say this was the kind of motivation for the papers that came next, which was Witten's paper in 2007, and Maloney Witten in 2008, and Maloney Keller in 2014. The last few have come to be known as MWK. So what they wanted to do was to treat the non-supersymmetric three-dimensional Einstein-Hilbert theory and see if they could construct a partition function for that theory in the semi-classical limit in the same way. Enumerate the smooth classical saddles of the pure 3D gravity, and sum over all of them dressed with the fluctuations of the graviton around these saddles. This thing is manifestly SL2Z invariant, but it has other issues. So it could be done for the elliptic genus. The question was, can it be done in this setting for a theory which we don't quite know exists? They constructed this thing. Some of the smooth classical saddles. And more explicitly, this ends up being a sum over SL2Z images of the character of ADS3 appropriately transformed. So each term in this sum is a different BTZ black hole. One of the terms is the ADS3 vacuum. And these characters are one of exact. They are just the Virasoro characters. Right, so this in particular is the Virasoro vacuum character. So let's write it like that. And that thing is one loop exact. So this is SL2Z invariant. It contains the vacuum. It contains all the black holes that the theory ought to contain. And then you can ask for the properties of this thing. Okay, so what are the properties? Let me change those to dots so I can use a plus-minus system here. So there are some good things and some bad things. That's a time-dependent statement. Some things that are now seen as good used to be seen as bad. So what are they? So this thing is modular invariant, right? It is geometric in that it can be written as a sum over the saddle points in the semi-classical approximation. Okay. Those things are good, but it suffers from some issues. The first is that the sum is actually divergent. MWK regularize it. They argue that the regularization is perhaps unique, or at least there's a natural one. But nevertheless, ideally, it would not be divergent. I think we can agree. More obviously bad to a bootstrapper is that the density of states is negative. Now, this was first seen in a way that turned out to matter less than a way that was discovered later by Yifan and friends. Okay. So, the first claim is that the density of states in the scalar sector, well, there's the vacuum. And then there's, upon regularizing this divergence in the way that they describe, a -6 number of states exactly at the threshold. Okay. That's bad. You can cure it by adding something to the partition function to make it go away, but that thing you're adding doesn't have a bulk half-integral interpretation. More seriously, Yifan and friends, Benjamin, Uguri, Xiao, and Wang, showed that there's this near extremal regime where there's negativity in the partition function as well. Okay. Can people see down here? This one? Okay. So, if you look in the regime where h goes to c minus 1 over 24, and h bar goes to infinity, so this is a large spin regime. Okay. And c minus 1 over 24 is the black hole threshold on the left. So this is sometimes called a near extremal regime because the VTT black hole that corresponds to this set of dimensions is highly spin. In this regime, the density of states, so a large spin, as t goes to 0, is negative, where I'm going to define little t as what's sometimes called a reduced twist, which is h minus c minus 1 over 24. So let me continue this analysis in a place with a little more space. So we'll address this momentarily, but right, this was sort of fixed on the spot back in the day. This problem, which was pointed out in 2018 or 19, sort of more severe, a fix was kind of proposed, and then we'll talk about that fix a bit more in a moment. But it's an issue for unitarity.
Are these problems dependent on how you regularize the divergent sum?
Yeah, good question. So this -6, yes, it arises from, so you have a divergent sum, you regularize it in, you could say it's some canonical way, and then this -6 pops out. But this thing is there sort of whether you like it or not. I don't know of a way to regularize that sum that doesn't contain this. Yeah, this is a bigger problem. Yeah. Perhaps I should say that the fact that this divergence is sort of easy to see. So you end up having to sum over co-prime integers something like this. Okay. This would define an Eisenstein series. The sum you have to do has a factor of q in it, but as far as the convergence is concerned, you can think of this as a toy example. And we're summing over c and d. This is squared in the denominator. This will diverge. Okay. Yeah. And then the other feature, which, well, let's give this a plus minus because it's not, it hasn't been clear whether this is good or bad, is that the density of states is continuous. So in particular, on this kind of diagram again, here's the vacuum. Here is c minus 1 over 12, and then let's continue over. Now, at first, this was seen as bad. So it's in the Maloney Whitten paper. They said this doesn't have a Q expansion. This can't be the partition function of some dual C of T. This is bad. Okay. Now, if you were at Tom's lectures last week, then you would say, oh well, actually maybe this isn't bad. This is good because averaging, and so some average is being taken, and so that's why it's continuous. But, well, maybe you don't like that. And, well, we'll return to that in a second. So, those are the features of this thing. Yeah, okay. So any questions? All right, I'll try to be quick, get to the new stuff. So there are ways out of this. And this will bring us to present day. The first is to add matter. Benjamin, Collier, and Maloney noted that if you add conical defects, there are various ways to do this. This fixes the negativity, but it moves the spectrum, the gap down to C-1/16. Okay. So it's still of order C. In that sense, it's a sort of Planckian gap, but in the strict sense, if added matter, it's not pure in the strict sense. Perhaps one doesn't care about that. That's fair enough. The partition function is still also divergent because it's constructed in this same way, where now you've just added a few other sort of non-smooth saddles that represent massive particles back reacting. But at least they're very massive, so it has that going for it. But we'd like to see if we can do something different. The other way is to add off-shell configurations. So this was the point of view of Max Venturiacci, who, inspired by developments in JT gravity and the fact that you can take a kind of limit of a 2D CFT which has a sector which behaves like JT in the bulk. There's a certain set of off-shell configurations that they propose one could add, which would actually fix this negativity at large spin and shift the gap by a very small amount. So this is non-perturbatively small in J and C, which are both large. So now the gap is at large J. The gap in twist is almost C-1/12, just with some tiny shift. The negativity is gone. But the college was to add some configurations to this path integral. They describe this in 2D language. They propose a 3D calculation to do that would reproduce this. The downside is that, well, no one's done that calculation. So it's not explicit, and in particular, the SL2Z variance of the resulting thing is not standing any question. It also doesn't address the scalar gap, so we don't really know truly what the gap in dimension is, because this is an argument that contains the large spin spectrum of the theory. And if you were to do this sum, it's not totally clear what you would find in the scalar sector. And it still has this divergence problem, presumably, because in addition to that divergence sum over saddles, you're adding other stuff. Okay, so this is a somewhat dry recollection of things that have happened to this point. But I think I've laid out the relevant major developments. Are there any questions?
Sure. So
Yes.
if I'm correctly, so in this Maxwell Toriachi, the geometry that they proposed are these cipher manifolds, and you're saying from the 2D perspective, they're not related to the, well, they're just not related to the defects on the other side, right?
Correct. Yeah, these look like defects in the 2D JT
Yeah,
sense,
2D
but these are
defects,
3D AS3. So this is like 3D matter.
That's right.
This is 3D, I don't quite know what, but
Yeah.
not matter.
Yeah.
Okay, so there's another way out. As I suggested before, this will require us to enlarge the chiral algebra a little bit by adding currents, but these are just boundary degrees of freedom. And a lot of these problems will be fixed in a kind of simple way, but let's explore it and see where it leads. Okay. So first let me make two conceptual points. The first is that the problem with MWK is not that it has negativity, is that it has a lot of negativity. So what I mean by that, let's define nj as the absolute value of the integral in this negative region of the density of states. So the density of states is negative in some region, then it becomes positive again. Let's ask, what's the total number of negative states in that region? Where the normalization of rho you can think of as being set by the fact that the vacuum appears with multiplicity 1. So what they find is that in fact, this grows like that. Okay. So this is exponentially large in the entropy in the spin J sector. I'm going to take the Carty formula before, but you can think of this as an e to the c or an e to the s problem. Okay. That's a lot. The second conceptual point is that we're writing down something which is a sum over saddles, and we're trying to interpret it as a semi-classical gravity partition function. But we should only take such a thing seriously up to e to the minus s corrections. Because lots of things could happen at e to the minus s order. In the sum over saddles, so e to the minus s corrections to the, say, density of states and OPE data. When we write down a sum over saddles, this is really only justified in an approximation where we're imagining working to all orders in 1 over c or 1 over s, but allowing for the possibility that non-perturbative e to the minus s corrections can augment that answer. So when you take an ansatz like this, you should only take it seriously above resolutions of order e to the minus s. So we should work at scales greater e to the minus s. In other words, what we really want in a semi-classical limit from the sum over saddles kind of construction is to construct the gravitational to all orders in 1 over c, allowing for possible e to the minus s effects later. Given this, one should not be afraid of the continuum. So if there's a continuum in the spectrum above some gap, we don't have to necessarily think of this as arising from some average over theories or over CFT data. It really can just arise as the artifact of working to all orders in 1 over c expansion, but not beyond. In a chaotic theory, like we expect any theory dual to pure gravity to be, the asymptotic level spacing is e to the minus s. So you wash out over that, you see a continuum. Okay. The other side of what I just said is that if one constructs a partition function which has negativity, but only e to the minus s amount of it, that's something one can tolerate in the construction of a unitary partition function to all orders in 1 over c expansion. So the proposal just add currents. So we're going to consider CFTs with chiral algebra A times A bar. I'm taking A equals A bar, and I'm going to take A to be the B times 0 squared. The total central charge of this theory is C plus D, where D comes from the currents and C comes from the rest. So the stress tensor has a pseudo-R piece, and then it has a non-pseudo-R piece, and that has central charge C. The chiral algebra factorizes, but the theory doesn't. The space of theories with this chiral algebra is presumably just as wild as the space of theories with just 0, 0, in spite of the extra currents. And I mean that in the sense of working with the primary spectrum, say, with respect to A, not just VRC. Something we should always do, as more in Cyberg talks. So the proposal is the following. Take the same sum over vacuum characters as before, only now for this algebra. From this we can extract a density of states.
Sorry, what is D? Capital D?
Capital D is the number of U1s.
But it can be any number.
Yeah, so we'll in the end see that we want D greater than 1. But for now it can be any number. Yeah. So we can extract from this a density of states, rho h h bar, by processing this sum. This can be written in terms of modular kernels for the characters of this Carrel algebra. This, of course, is just a very trivial modification of the Virasoro case, because when you add a bunch of U1s, the vacuum character just picks up some 1 over etas. Right, it's abelian, so that's it. And so, if we study the primary partition function, P, with respect to the full algebra, okay, we can write this as a sum over elements gamma, the same sum as before, in the following way. Where we're really, well, let's try to look this imaginary part of gamma tau. So there's a d plus 1 over 2 here in the exponent. This just comes from stripping off the eta functions you get from here. So this is the sum that we really want to do. The MWK case has d equals 0. Otherwise, it's the same sum. All right. Now,
So what are the extra labels there? A and P?
sorry, which extra labels?
Just said A, P.
Oh, Z. Good. So this is the primary partition function for the Carrel algebra A given here. Okay. So Z P A is Z times mu tau
Why do you call it primary?
because stripping off this factor allows us to focus on just the primary density of states with respect to the full Carrel algebra. So in the same way that if you just have
Oh, it's like if you do a state expansion and you divide away the thing.
yeah, I'm getting rid of the descendants. Yep. So this has some nice, without doing any more work, this has some nice effects. So this actually converges for d greater than 1. Okay. In fact, this is a physical interpretation of the regulator that MWK originally used. The way they compute the divergent sum is by looking at an expression like this and then taking d to 0 at the end. But in fact, take d to be physical, and you get a convergent sum. Yeah. Yeah, so d equals 1 sort of on the threshold. It doesn't converge, but it's not as badly divergent.
So is there any resolution scenario?
Well, you could regularize it, but here I'm going for something better, which is I want something truly convergent. And as we'll see in a moment, really in just a moment, the negativity is also better if you take d greater than 1. So that's what I'm about to say. For this theory, the negativity is also exponentially small. Okay. So, schematic. If we take this density of states in the bar spin regime, and the external limit, where it's called t is h minus 124. Then what happens now is that this looks morally like this. So I'm suppressing coefficients and some functions. There's a minus sign here, indicating that the coefficient of this thing can be negative. And so there's a regime of negativity. So this happens for some scale minus j 4. But then if you ask how much there is, in fact, what you get is exponentially small. It goes like e to the minus d minus 1 times cj over 24. Perhaps there's a constant missing, but the dependence is exact here. So for d equals 1, it's large. For d equals 0, rather, it's large. For d equals 1, the exponent goes away. It turns out to be power law suppressed. But for any number of currents greater than 1, this is exponentially small. And if you're trying to construct a semi-classical partition function to all orders in 1 over c, but not beyond, that vanishes.
Sorry, I have a very naive question.
Yes, please.
Summation is over some saddles or some gravitational theory, or
This summation?
yeah.
So think of this as the sum over smooth classical saddles in a bulk theory with this asymptotic symmetry algebra. But for now, we're just constructing this as an Esselthusian invariant sum over this vacuum character and asking what it looks like. But yes, from the bulk point of view, it is the original interpretation in terms of a sum over the complete space of smooth classical saddles of, in this case, and I'm jumping ahead a little bit here, Einstein-Hilbert coupled to d U1 Schmidt-Simons gauge fields on left and right.
But this construction is purely from character. You require to be Aristotelian environment.
Yeah, so I'm just saying, study this thing, then let's ask what it looks like in a large C limit. Of course, the whole motivation is this is just a small tweak of the original logic, but we want to restore the logic and see if we can construct something consistent with it.
So Eric,
Yeah.
do the currents give additional saddles, or they just modify the only determinant?
They just modify the determinant. Yeah. Okay. So, let's draw a picture.
If the U1 were to be compact, there would be additional saddles.
Which ones?
If U1 were to be compact,
Right. Which ones?
sorry, I was just saying that if U1 were to be compact,
Yeah.
just related to Sudo's question, there may be additional saddles.
Yeah, I'm asking what you have in mind.
Well, I'm not sure the Wilson line, for example.
Yeah, so indeed, it's
Not
not
here
compact.
the trivial saddle with the base field.
Yeah,
Well, then you go to 0, just computing the 1.
yeah. So here another way to say it is that we're computing the unflavored partition function, which is blind to the spectrum of charges. The spectrum is continuous, consistent with a non-compact
Yeah.
U1, and that's the interpretation I think this is. Okay, so it's convergent, the negativity is exponentially small, and the spectrum is nevertheless continuous, but as I explained before, this is something that is okay if we just want to construct something to all orders in semi-classical expansion in G. So let's look at the spectrum a little bit more. We're going to look at the spectrum of twist. So we can treat all J simultaneously. The results are pretty uniform in spin. So this is not the SL2Z tau. Okay. So here's 0. And there's a gap to C minus 1 over 12. And there's a continuum. And we can talk about the gap in a few different ways. So literally speaking, the gap is to C minus 1 over 12. But then, in the same way that in the Narain story, one integrates the density of states until you get up to one state, and you can think of this as a notion of gap in the presence of a continuum. We can also do that here, if we like. So let's call this C minus 1 over 12 plus 2 T gap. T gap is defined as the density of states in the string phase sector. Okay, so there are different regimes that we can study. And the one which reflects the language I've been using is the regime where C is much greater than D. Okay, so for finite D, a finite number of U1 currents, you take C large. This is a large total central charge limit. Okay, so in this regime, this T gap is much less than 1, and the gap in the spectrum is C over 12 plus corrections. We can also consider a regime where D is much greater than C. So if D is large and C is fixed, in this case, T gap goes to D over 4 pi E. And since C is, say, order 1 and D is large, this reproduces the gap in the average Lorraine partition function at large central charge. We're not literally recovering the average Lorraine partition function because there's this Virasoro piece. And so in particular, this 1 minus q, this null state, is there, and there's this extra piece of the central charge C. But from the spectral point of view, the gap looks like the Lorraine gap at large D. We'll come back to that in a little bit. We can also consider a double scaling regime, where if D over C is fixed, and this interpolates between these two. What you find is the T gap, and I think I'm getting the coefficients correct. We call this ratio x. Then this is d over x times the Lambert W function. So this thing is the solution to this equation. At small x, you get back this. At large x, you get back this. And this gives you some interpolating function between the two. So let's zoom out and ask what we've achieved, and interpret this from a bulk point of view, and then microscopically from a boundary point of view.
Doesn't C need to be large for the saddle point approximation to be valid?
If you're thinking of it in terms of the graviton, then yes. But I only want you to think that way when C is large. When D is large, the total central charge is large. And the bulk theory, in that case, should not be semi-classical Einstein-Hilbert coupled to some number of currents. It's this exotic U1 gravity coupled semi-holographically to some Virasoro sector. So, indeed. I'm more interested in the large C regime from a certain point of view, but there's some nice interpolation between different bulk descriptions as you dial C and D. So, here, the claim is that this is a candidate partition function in a semi-classical limit to all orders in P Newton for pure Einstein-Hilbert gravity coupled to U1 to the D times U1 to the D bar to a Simon's gauge phase. In this limit, the graviton is a fundamental particle in the bulk. Really, it's a boundary graviton, but that's the usual story in 3D gravity. And the gap is C minus 1 over 12 plus corrections. Okay. Now, in the large D limit, the bulk interpretation of this partition function should be that of U1 gravity in the same sense as in the Lorraine story, but coupled to a semi-holographic your Soros sector, and by this I mean in the sense of Faulkner and Polchinski, where you have some sort of small, say small central charge, not strongly coupled sector of the theory, which is not realized by the geometry in the bulk, but couples to it. In this limit, the graviton should be thought of as composite. This is the current dominated part of the theory. So it's composite in the same sense as in the U1 gravity proposal of the average Narian theory. And T gap is D E plus equations. So let me make some comments, and of course, please ask me questions. Okay, got about 10 minutes, is that right?
Yes.
Okay, so some comments. The first is that this construction is convergent, and D greater than 1. Geometric in the sense of being able to write it as a sum of recitals, at least in the large C limit. Unitary, this is 2Z invariant, and it's here. So in the spectral sense defined here. Now, these statements, in particular this one, are subject to e to the minus s corrections, but the point is not to take the construction seriously to that order, because you shouldn't do that when trying to construct something semi-classical, a leading approximation, and especially if it's got a sum over saddles interpretation. The second comment is that, well, we can look at higher genus partition functions and ask about their convergence. So these are convergent for G less than D. So there's a bound on the genus at fixed D. Now we're talking about convergence. That's something that perhaps is not the most important criterion to you, but nevertheless, if it is, and there's good reason to want this to not be divergent as well if you take the point of view that I took earlier, there's a parametric regime where we can take large C and then take large D, where these higher genus partition functions are convergent for a parametrically large range of genera, while nevertheless maintaining the gap being C over 12, as discussed before. Okay, so here we've talked about the effective bulk description of what this partition function, of how this partition function should be thought of. That's our proposal. And now we can ask about the microscopic CFT interpretation. And this is interesting. There are a few possibilities. They might be equivalent, and they might also give us some hints into this question of whether semi-classical gravity is really to be taken seriously as a solution of Bootstrap equations, or just as a solution of some kind of effective large C Bootstrap. So we can, for example, follow the interpretation of Chandra et al., as discussed last week by Tom, and think of this as capturing this partition function, this density of states, as capturing a kind of average over CFT data. So here I've just talked about the density of states. We could talk about the OP coefficients if you wanted. But in this generalized average sense, perhaps this is just constructing a partition function which captures some ensemble which can then be thought of as what the bulk theory is describing, with no contact with the space of actual bona fide CFTs with this chiral algebra at large C. So, in that story, there was no claim that if you average over the space of Virasoro CFTs at large C, you actually land on their ensemble. The construction is, say, bottom up. However, here we've constructed something which has all of these properties, unlike the ensemble in that case, which was not SL2Z invariant, just S invariant. Perhaps that's something one can live with, but the whole point of the story, in a sense, is that full SL2Z has some tension with unitarity that's hard to resolve. So because it checks all the boxes, perhaps we should interpret this in the way that we traditionally would want to, which is a large total central charge limit of some sequence, let's call it T, C total, of U1 to the D times Virasoro. So in other words, think of this as the large C limit of some sequence of microscopic consistent partition functions. This interpretation seems available to us. And in fact, perhaps we should think of these two things as equivalent. So one can imagine obtaining this kind of ensemble of data by actually averaging over this space, or just looking at a single element of this space. When that happens, the theory is called self-averaging, which is a reasonable thing to expect for large N chaotic theories. Now, there's something interesting about this interpretation, which goes back to a paper of Yifan, Nathan Benjamin, Naguri, and Xiao, not the one I mentioned before, a different one, which is the following. If you look at a finite central charge theory with the U1 times Virasoro chiral algebra on the left and right, so here in that paper they talked about a single U1, but it generalizes, then they argued, under a set of assumptions, that the twist gap is actually 0. The assumptions are that the CFT has a discrete spectrum, and that the spectrum is finitely generated. What that means is that there's a finite set of primaries whose successive OPEs generate all of the primaries in the theory. This has not been proven to hold for finite central charge CFTs for any chiral algebra, but under this assumption, plus discreteness, the twist gap was shown to be 0. Here we've constructed something which is not discrete, but the spectrum is continuous. We're taking a large central charge limit, thinking of it as a large central charge partition function. And in that limit, there's certainly no reason to expect that the spectrum is finitely generated. And so the conclusion doesn't apply, which is a point that they pointed out in their paper with respect to this particular example of D, the Poincare sum over this vacuum character. So that puts you in an interesting position, because on the one hand, we'd like to interpret this as a large C limit of a sequence because it has all the properties we would want of a theory like that. But it looks very different than a theory at some large but finite C is allowed to look. And so this is a kind of realization of some ideas floating around lately, that when we work in a large C limit, we need to be very careful about what kind of conditions we impose and what problem we think we're solving. So we need to be careful in large C. And so one might say that, right, so if we sort of think of the space of central charges, complex central charges, as a Riemann sphere, but this is the point of infinity, let's say this is 1 or something. When we talk about bona fide quantum gravity, what we'd really like to understand is how, at some finite central charge, the theory works. Okay. Now, holographic approaches start from here and sort of work down. Right? You do a 1 over C expansion around some generalized free field theory in the bulk, say, you include the graviton, whereas the modular bootstrap point of view is sort of working up from here. Right? And neither of them is very good at understanding what a theory of large but finite central charge looks like. So the partition function I've constructed can simultaneously be thought of as a large C limit of a sequence, a limit in which the argument that leads to vanishing twist gap breaks down. But at the same time, to complete it to a large but finite C theory, a truly quantum theory, there would need to be zero twist states added if you accept the assumptions of that paper. So I personally find this interesting because it's a concrete example where the infinite C and expansion around infinite C theory and the large but finite C theory must look, or at least can look, very different. And so this bulk theory that I'm describing here is a solution to a problem that's kind of localized around large C, but to make it a truly quantum theory, sensitive to e to the minus s corrections and beyond, the partition function needs some other ingredients. So let me conclude, and I'll just conclude by reiterating this last point, that I think if we want to really understand quantum gravity in ADS3 for finite, even if infinitesimally small, or close to infinitesimally small values of Newton's constant, then we really need to contend with e to the minus s effects. Perhaps this is something that the resurgence of the semi-classical gravitational path-linear rule can help us understand. And even in that case, it's not always true that we can use this to understand the large but finite C theory, the finite G Newton theory. But understanding this set of questions, I think, is important to asking whether our semi-classical bulk theories of gravity can actually be, let's say, smoothly completable into quantum theories, and if not, what kind of ingredients are required to do so. But in the meantime, this construction can be thought of as a construction that, to all orders in 1 over C expansion, satisfies all the requirements one would want of a semi-classical theory of gravity. So let me stop there.
Questions? So now your question. So do I think of this U1 to the D as method, extra method that I added to pure gravity, or?
I would say no, or at least as a very special kind of matter. I mean, I would say that, you know, it's a pure gravity with, you fix the chiral algebra, and then you try to construct the pure gravity theory. Here we're taking the chiral algebra not just to be zero, but to have U1s, and then the theory we constructed is pure in the sense of having no matter. To say it another way, we've added some special matter, which is just localized at the boundary. These are Folkman-Simons gauge fields. There's no propagating degrees of freedom. So in that sense, they differ from light fields or even from conical defects.
Mm-hmm. But in the same way that gravity in 3 dimensions is topological and it's all about identifications, these U1s, don't they suffer from the same thing, that naively it's all topological, but then globally there could be things? Maybe this is related to...
Yeah, I think this is related to the comments Yvonne was making earlier. But yeah, I would say this is a virtue. The topological nature of the bulk theory is what allows us to call it, that's what you would want in a pure classical theory of gravity. Yeah.
But what would be the observations of this? So the statement would be that from the bulk point of view, I solve the same Einstein equations, everything is exactly the same, and these modes in practice don't exist, they are just at the boundary.
Yeah, they fluctuate around the solutions, but yeah, that's their, in this construction of the partition function, that is their lone contribution.
But are there new observables in this theory, like Wilson lines or something that I could construct out of the Schoen-Simons and semi-classically measure this?
Yes, and so for example, you could study, I mean, there's a proposal one could make for the partition function graded by, fugacity for the charge, And then, so any unshots for that would have to reproduce the spectrum of charged BTC black holes if you wanted to make contact with free gravity with currents. I think it wouldn't be hard to do that. We just looked at the torus partition function. But yeah, with the gauge field, you can then do extra things. But here we're just looking at the zeroth order observable. Is there a question over there?
Yeah, just how did you get to the condition on convergence for a higher condition?
Oh, yeah. So this is something. The paper by Maloney and Witten from 2020 has a nice treatment of this with this Lorraine story. And as I mentioned before, you can think of the kinds of SL2Z sums that appear in these calculations as generalizations of the Poincare representation of Eisenstein series. For higher genus, there are higher genus Eisensteins that generalize this, and they have a nice discussion in their paper where you can see rather quickly that this condition follows, where in the Lorraine story, it's U1 to the D. Here it's U1 to the D plus a Virasoro, so there's like a shift by one of the convergence condition. But yeah, the proposal for the higher genus partition functions is essentially the obvious one, except where you just have some more factors of the relevant determinant of a period matrix. Whereas here it's in tau, in the higher genus case, it is a function of all the moduli of the surface, but it's got this form which generalizes the higher genus Eisenstein series, and convergence is manifest in the same way as in their paper. Sure. Yeah.
From the point of view of just fixing the Maloney-Witten partition function, it seems like U1 to the D is just a technically simpler thing to do. Would it work with non-abelian currents, or?
Yeah, so with non-abelian currents, what happens is that if you were to sum over the vacuum modules, you'd have null states you have to worry about. And then the argument for whether it's positive is harder. You just have to work a bit harder. So you have to characterize how much negativity there is. There will be some. And when you add more null states, you should start worrying about adding more negativity because there are minus signs in the thing you're summing over. But then the question from my point of view is, if you're trying to construct this semi-classically, is the resulting negativity exponentially small or not? And one would have to work. We haven't done that calculation, but yeah, the U1 to the D is technically easiest, in part because the numerator of the character is trivial.
Are there more questions? Not, let's thank Eric.